Alright, so this little part of the lesson is going to take you through the derivation of the basic model that we use for bending stress. You're going to want to have your sponge beam available to you because that's going to play a critical role as we go forward. Right? There's a whole lot of really crucial things here to take note of. You should read through these lesson comments. Those are important, but particularly have at hand as you go through this page that talks about the arc length formula, reminds you of Hooke's law, definition of strain, what the Y might or might not represent here. We're going to have to be careful about that because different textbooks mean this in different ways. So this is a tricky one sometimes, right? So other textbooks will, for the beam's transverse deflection, will use V. I prefer V instead of Y, but you're going to be more used to Y, especially when you look at the definition of curvature, that being the second derivative of any function, and then divided by this square root of 1 plus the first derivative squared, which ultimately, for small deflection, will come down to this, hey, just curvature is the same thing as approximately the second derivative, period, because the slopes are small, so they go away when they're squared, and that will become just 1 in the denominator, right? So a lot of textbooks use V for the function of the transverse deflection because Y will tend to mean something else in a different kind of context. And then down here below, have at hand how we find centroids, first moment of areas, and how we find second moments of area, and that those are that so-called moment of inertia. All that you have to have sort of at hand as we get into this model about stresses and the moments that are causing those stresses, right? So go back to your sponge beam and put it into bending where the red parallel lines are on the face or the side face of the beam, right? And you can see how we're bending now. If we bend even more, notice that the relative orientation of those red lines begins to change, and that they're not even straight lines anymore. They'd be, wow, when we get these extreme kinds of bending deformations. Now, when was the last time you actually saw a beam that you walked across bend that much? I hope never, because they don't tend to. Instead, in a relative scale, they'll tend to bend maybe that much, and that would even be a lot. You're barely even seeing that. So notice how these red lines that start off parallel remain parallel after we bend. I'll exaggerate this a little bit so you can see it, right? So they're still straight, and they're still parallel. Well, no, they're not. Oh, hey, they're not parallel at all, right? And note, they tend to actually seem like they're kind of pointing towards the same place, right? Let's go back to no deformation, right? So now we'll put again a little bit of bending moment on there, a little curvature, right? And hey, you know, on one side those are getting squeezed, on the other side they're pulling apart. Oh, hey, there's some really important things going on here, right? So what we're going to make as our hypothesis here is that A, we're going to talk about elastic action. That immediately brings in, of course, Hooke's law, that sigma equals E epsilon is going to be a consequence of that. Right? We're also going to look at only small deformations, right? Because we don't want to see the kinds of things that are happening way out in there. And actually there's a mathematical significance of that will show up here very shortly. And then we're also going to say, you know, we don't want to start looking at warping of the cross-section, and that statement is that plane sections remain plane. Now what we're talking about here is you're seeing here the side or the edge of the plane, and as we have bending, then that plane remains a plane. It may rotate, but it's not going to warp and become somehow curved or anything like that. Right? Those are the critical key pieces. Now, down here on this drawing, let's put all this into action. Right, so we're going to have some bending moments, the same on both ends, so we're in pure bending here. And note that this little dashed line right here, that represents back in our sponge beam this sort of blue-greenish kind of line that goes along somewhere in the middle-ish of the beam. We'll discover where that really is later. Okay, so before we bend it, it's nice and straight, then we begin to put that moment on, and it begins to get curved. And notice how all those lines, those red lines, tended to point in the same location. So if you come up here and you extend these, we're going to say that's one red line, that's another red line. They all come up, intersect at one little point, right? And that radius then, all the way down to wherever that little dashed line is, that's our radius rho that's associated with the curvature. Right? So we go back, note that that line, that dashed middle line, is sort of where you don't, that's a transition between that spreading apart down on the bottom of it or the getting squeezed together up at the top. Right? Now we've got this little angle, we're taking a tiny little dx segment. Right now along this arc, that would be ds, and the projection of that down on the horizontal axis would be dx. That small deformation theory, we're going to say that that arc length is approximately the same as our dx, or if you want to say it the other way around, but the ds is the exact, the dx is the approximation part of this. Right? So that's a small portion of this, and then we just go and apply what we already know. Hey, arc length, that's equal to, let's see, the arc length s equals the radius times the angle. Well, at our incremental level then, that's going to be that our arc length ds is equal to our radius rho times our angle d theta, of course in radians. And then because of the small angle approximation, that would mean that that's approximately equal to dx. Right? Now strain, remember, is going to be some sort of change in length, or d delta, divided by some sort of original length. Right? So dx is our original length. Now what deformation or change in length are we really talking about? Right? So now let's come up to here. ds, where I've got it positioned right here, has no change. Remember on top we had shortening, that's what this big bold line shows. Now, oh hey, look, this dashed line here is parallel to this one over here. Those are the two originally parallel red lines. After bending, then that has rotated over, swept through the same angle, d theta, as this one right here. Right? So this little, at a distance up, that's your actual y value now, at a distance up from this neutral location, then we have some amount of then change in length. Now notice that is a change in length that got shorter. So what we're going to do is we're going to call that minus d delta over dx. Positive y, oops, sorry, got ahead of myself. Leave that there. Positive y, though, induces a minus d delta. Now, right? Well, we'll keep, hold on for a second here. Let's see, how does this work? Oh, hey, there's a triangle there, right? And that triangle has one side d delta, has the other side y up from the neutral axis to the point of interest, and that angle is d theta. Right? Now, right triangle theory, tangent of d theta equals opposite over adjacent. Okay. Now, small angle theory says that's about the same as d theta. So d delta is approximately equal to y times d theta. Now, here's the thing we got to be a little bit careful of, and that's signs. This is, alright, got a little ahead of myself here just a little bit ago. Right? And that is, you're going to insert an arbitrary minus sign when we put in the d delta. We get minus y d theta over dx, because we have a positive y implies a shortening or a negative deformation, and this is with positive bending moment. Right? Remember, positive bending moment tends to create smiley face curvatures in the U.S. sign convention. Right? It's a mouthful already, isn't it? All right, well, we're going to take this even further, because up here now we have d theta dx is equal to 1 over rho. Take that over there, take that over there. That's how we got that. Substitute that in, and we get a pretty important equation which says that the strain is equal to minus y over rho. And that's a critical one. Nice and simple looking. Now curvature, remember, we said that was the same thing as 1 over the radius of curvature. And so that means that the strain is equal to minus y times kappa. Again, positive curvature. Hey, you know, if we were plotting the deflected shape of the beam, then concave up would be this smiley face, and that curvature would be the second derivative of the function that described that deflected position along this neutral position. Right, so that's how that all begins to work out. And what we're going to derive on the next page here is that moment, the amount of this moment, is equal to E times I times the curvature. E, the elastic modulus, as in Hooke's law, I, the second moment of area of the cross section, and kappa, the curvature. Right? This is all built up. We're going to need all of these, have these at hand as we go to the next page and start doing some statics and also a little bit of mechanics of materials. Right, so now what you want to kind of get used to here is that in this view we've got the actual cross section. So that means we're looking at this beam, and then we look now at this end right there. That's what we got here. This view, we're going to look at the side view of the strains. So that's like looking at the side here. Right? Now remember, this is elastic behavior, and we have said that we're going to assume plane sections remain plane. So after deformation, then those d deltas, and then divided by the original length to get us to strains, will be a linear relationship. We've got compression on the top, and we've got tension on the bottom. Now this is an asymmetric cross-section, so the distances here from that neutral location, right, that's the neutral surface, are going to not necessarily be the same. Right? So we'll have C to the top and then C to the bottom. Not necessarily equal to each other. Right? And so as we go then from taking the strain and thinking about stress, remember Hooke's law, elastic behavior, all we have to do is multiply by the elastic modulus, and we have a stress diagram. So, hey, if the strain is a linear variation throughout, well, so will the stress. It'll just be in a larger scale. Right, so we've got our, oh hey, did you notice here? We got tension on the bottom, compression on the top, and the maximum stress corresponds with the maximum strain, and it's at the outer fibers. Now, if it's asymmetric cross-section, then we won't have the same max compressive stress as we do tensile stress. Right, now there's even a little bit more here to be thinking about, but let's catch up on what we've got written down here below. Max strain is at y equal to c top or y equal to c bottom. And you're like, what's y? Well, remember from the previous page, y was our distance up from the neutral axis to the point of interest. Here, that point of interest is all the way up at the top, and so this is a positive value for y is going up. Right? Generally, then, our strain then would be just a linear proportionality as we go along there, but also keep in mind that the strain is equal to minus y times the curvature. The max stress, of course, also at y equals c top or c bottom. the stress just anywhere, sigma then would be equal to E epsilon or minus Y E kappa. Ordered it that way for a particular reason that you'll see here coming up. Alright, so now let's start doing some real statics here. And so at a distance y up from the neutral axis, there's your strain value and there's your stress value, right? Again, at a distance y up from the neutral axis, right? So a stress times the little differential area that we have here, it's a normal stress, so normal stress times the dA would be our differential force. And those stresses vary everywhere across the cross-section, so when we go due to this equilibrium, we're going to need to do some integration, right? The differential force that we're going to sum up, all the little sigma times dAs, then we can plug in here that, okay, our stress is equal to minus YE kappa times dA. Right? Now, if we have homogeneous material, it means the same material throughout without any variation in its properties, then the E is a constant across this cross-section and can be taken away. And the curvature is just how much at a specific location we have what the second derivative of this deflected shape is right at that one spot. So it doesn't vary across the cross-section either. That's also sort of a plane sections remain plane parts. So it can come out of the integral. And we're left with then minus y times dA. Now the minus sign is not particularly important here. That's all going to be set equal to 0 because it's axial equilibrium. Note that is the first moment of area. Since the kappa is not 0 because we have real bending, real curvature, and E is not 0 because we have a real material that has actual stiffness, that means this integral must be 0. And since integral y dA equals 0, that tells us that this neutral surface or neutral axis is at the geometric centroid of the cross-section. And that's a pretty important result to had, because before now we just said, well, it's the transition between tension and compression within the cross-section. And now we know where exactly it's located, right? We didn't prescribe it ahead of time. We just said, we know there's tension on one side, compression on the other, but we don't know where it's at, and we find out where it's at through this axial equilibrium. Right? Now, one more drawing I want to add here that might be a little bit helpful to help visualize what's going on is, let's extend this line on out, and it goes right through those words, the neutral surface, which is just fine. Put a little vertical bar here too, and so let's go back to this little differential force. That's just, again, at that one specific location. That would be dF, and that equals sigma times dA. So this would be the force resultant model. Let's put that in quotes now, for now. It's really I'm wrong about that. That's the stress result. Actually, I made that mistake on purpose because I want to emphasize we're taking the resultant of a stress. That's where the force is coming from. But hey, it's at a distance away from this neutral surface. Right? Now, this next part is going to get, well, it's a highly argumentative kind of next part. What we do is not the big deal. It's how we handle the signs that are sort of a big deal, right? We're going to sum moments of all these differential forces about the neutral axis, right? Now, when you look at what's going on here, we're bending this thing, bending, right? We're talking about what was the internal moment that caused that thing to want to kind of rotate. And so that means that we want to integrate all the tiny differential moments. Well, what are you talking about? I'm talking about the moment of this differential force, dF times its perpendicular distance. Now, this is where I don't particularly like this, but you'll see some people put a little minus sign. They'll call this that in a global mathematical model that this is actually this rotation that I'm showing you is well, that's actually the right-hand rule, isn't it? But the thing is, if you had a positive stress, which would be tension, we don't. But if we had a positive stress, you'd go the other way. We have a compressive stress. And that's why we're going to add this another minus sign in here. It's a little unsatisfying, but what's really happening here is that we've got this situation with the American sign convention that we have positive up means compression, but we like to call compressive stresses negative, and yet that won't give us a counterclockwise right-hand rule rotation. Sound goofy, huh? Well, let's just work this out, and you'll see that it really is not that big a deal, that we're making this a lot harder than it really has to be. Right, so now we come in here, we got minus, we've got the dm, which is equal to the minus y times df, and df is itself sigma times dA. dA is just this little differential area, and hey, sigma equals minus ye kappa, and so we get a minus minus. See, it goes away. That's why people like this approach. It becomes plus y squared e kappa dA. And for the same reasons that e and kappa are constant and we pulled them out of the integral before, that are the same ones we do now, we have e kappa integral of y squared dA. Well, that is, by definition, the second moment of area. And because we know where y is referenced from, that's the neutral axis, which is located at the geometric centroid for elastic behavior, then that is the centroidal second moment of area. Right? That's going to be a key thing. So that gives us this moment curvature relationship, usually not written e kappa I. Instead, it's usually written as ei kappa. Right? Now, it's written that way because E is a material stiffness, EI is the bending rigidity of the cross-section. Right? Now, we're almost there. Almost. Right? And so, we have one last little part that we need to do to get to the most famous of expressions. The one that really matters here for us. Well, they all matter, but you're going to say this one really matters. Let's go back to our basic stress curvature relationship. Our bending stress equals minus ye kappa. Right? Now, we found out with moment curvature that, kappa is equal to m over ei. And so that means we go minus ye, substitute in m over ei, the e's cancel out, we rearrange the order of the terms, and we get minus my over I. I want to rewrite that in a very special way, and that is sigma equals minus plus my over I, bubble it, is the most crucial equation that we have. Right now I wrote it this way because positive y with a positive bending moment gives us compression on the top. If we go down below, then that would be a negative y times a negative, giving us the result of a positive stress. I know that's kind of goofy, right? So that's really weird, right? And people don't like that. So what we do is, or at least what I do, is I say, look, if I have positive bending moment, then I know I have compression on the top and I have tension on the bottom. If I have a frowny face or negative moment, then it's the opposite of that, and I don't really worry about this minus plus business going along. The Europeans don't like this either. They define things such that that's positive moment, that's hogging curvature, and that's negative moment. Well, that's weird. And so Americans don't like that, so we do it this other way. Well, let's see in the next videos about how we're going to go about applying these.